I think you will post it on the Blackboard as well.
Today?
I don't know, you will talk about it.
Yeah, please say it. We were doing this one too.
Yeah, hello. That's a one side. You have classical mechanics?
Classical mechanics?
How the value you have?
Quantum.
You have quantum?
No, sorry. Classical mechanics, qualified.
Yeah,
But
classical
not
mechanics.
Huh?
Classical mechanics you are in quantum?
No, I don't have qualified. Only classical.
You have only classical?
Yeah. You have the classical?
Yeah.
Sure, let's study. Okay.
Okay. Have you started to? Have you started? Okay.
This homework for you for the weekend. I already uploaded this one in the Blackboard and assignment.
Okay.
Yeah, you can see the colors and everything. It is very simple. So that's what we are going to do today, and you will understand. So both these problems we will discuss today.
We will discuss
Yes.
today. Okay.
They are not the same problem, single problem.
Yes. Okay.
Any questions from you? Last class, especially for you, it's okay, right? I just want to give a little, maybe sometimes when you see these things you don't get.
Yeah, I need to do some.
Yes, yeah, but you can come and see me if you need any help. Yeah. So last time we discussed about simple quantization experiments, right? In classically you never get these discrete levels, right? So in quantum mechanics, we can see how these quantum states are developing. These are discrete levels. That's how we explain all the hydrogen atom spectra and everything, right? So that's beautiful physics. You can see how they develop these orbitals. Everybody familiar with SPDF orbitals, right? So S, the L goes from 0 to 1, you have SL equals 0 means S orbital, D orbital, D, and so on. So most of the systems we are going to discuss in this class is SOP orbitals. Maybe few examples when we go to magnetism, D orbitals like transition metals. Other than that, you don't have to worry about that. I just want to give one last thing. So we talk about, remember everything about, oh, you are still getting me.
Oh, no. I'm good. You're good.
Oh, it's very hot here, right? Can you open some?
I have a microphone I want to test. No, it's okay. Oh, yeah.
You want me to put here?
Oh, no. No, this will be more imperfect.
Okay. Great.
Okay, thanks.
Yeah, okay. So then, like I said, so when you start really the solid state physics, we are going to talk about, actually it's all about developing the work function, right? So sorry, the wave function. And if you know the wave function, you can calculate the energy and things like that. So if you have this wave function psi, so you have to remember this is a complex number, right? So the wave function is a complex, you can write as something like AE, I, phi or something, it's a complex number coming here. So that means you can define something called the complex conjugate. Conjugate is basically this become minus psi phi, right? So this is AE. Wherever you have I, that becomes minus psi. So then we define something called the probability density. So this is a number, right? This is basically the psi times psi star. So that is basically, it becomes a psi star psi typically, it doesn't matter. Yeah. So you can see if you take this one, what you get here, a squared, when you multiply it becomes 1, right? So this is a number. So then this is a probability density. If you want total probability, that will be the psi star psi times, if it is three-dimensional, it is d squared r rho dv, whatever. If it is one-dimensional, it is simply dx, right? So that's the probability. We know if you do it from minus infinity to infinity, that's, you will find somewhere, right? So this has to be 1. Probability is 1 means you can definitely find it somewhere. Then also you can define something called the probability current. So that's defined as, you don't have to go through so much detail. I cross over 2m, this psi times, it's a derivative of psi star, then minus psi times, psi star times derivative of psi, right? So this is more like the probability current or something that propagates. So by taking this, you can easily show, probably everybody is familiar with this equation, right? Even in chemical engineering, we talk the what is the continuity equation. Yeah. So if you take the derivative of the grad of this j, if you take the time derivative of this one, they should be always same. This is very common concept in many areas. Even if you do the like mass transport or heat transport, this is same thing. So last thing, remember we talk about the this is the last slide. We talked about momentum and space, right? The Heisenberg principle, delta x times delta p, this should be. So we know if this is perfect, I think this cannot be perfect, right? There's uncertainty depending on which. If this is, if you can determine this one with more precision, this can only be do with less probability, right? Less precision. So this actually, if you look at in, everybody familiar with the Fourier transformation, going from one space to another space, you can easily do this one, real space to this momentum space, right? That's what this one. So this is exactly what we call the Fourier transformation, right? Going from one to other. So if I have something, say, in the real space, or position space we can say, if I have some kind of, say, wave packet or something like this, if that, I can represent that this x dependence, right? Usually you can write as this in terms of the momentum, but you are integrating over p, so then your answer will be only x dependent, right? So that is, so you can write pi p e I p x over across this one. So now if I want to get pi, what do? You inverse transform, right? You basically multiply this by e minus I, right? Here, like this one, then you do the integral, then you are integrating over x. So then your answer will be only as a function of p, right? So that you will get this basically the momentum transform, right? So you can see if I have, this is I think less certain, right? Because it can be anywhere here, but here you can see that is more certain, right? So certainty is better here. So always if I give you some position function, you can transform into momentum, or vice versa. If I give something in momentum, you just basically do this integral. I think we do this one in many things, right? Another thing is, I don't know, this is also very important. I'm familiar with eigenvalues, and yeah, so that's fine, right? If you have any operator, if you operate it on some, say, even in our case, mostly the wave function, right? So then you get some, so this is your operator, it can be your, say, the Hamiltonian, right? If you operate on your psi, so then if you get your answer with some number here, so with same wave function, So this eigenequation, right? So we call these are the eigenvalues, these eigenvectors, right? So most of the time, solid state physics is more like solving this kind of eigenequations, right? It can be really difficult if you look at many body system, but typically we are talking about few electron systems, so it shouldn't be too bad. So you can see here, if I have this operator theta operating on this one, I get this number. That's eigenvalue, right? This is eigen. Please remember that one. Then rather than writing this psi xt, then this psi star xt, sometimes we use this simple the Dirac notation. So you might see time to time this one. It's nothing like this psi xt. You basically write something like this one. We call the bra vector. So then psi star means, that's a conjugate, right? That is basically you write as this ket vector, right? So like this is just a notation. If you see something like this, you see what it means, right? For example, if I have this equation, so this means what? This psi operator on this psi, right? That means you have this psi vector, this one, then it operates from the left as this means psi star. So it's the same thing, right? So this is psi star means this ket vector, and psi means this bra vector. So same thing if you operate in the p, the momentum space is the same thing, right? Psi, it is in the momentum space still. This means this directly pi, this means the conjugate. So if you see something like that, don't get nervous. So it's a simple way to write it, that's all. Oh, another thing is average number. So if we want to find the average value with respect to a wave function, how do you calculate that? If I want average number of theta, so this means actually you just this theta value, that's what we write, this psi star, then psi, whatever you do here, 3-dimensionality is d cube or something. In 1-dimensional it is simply x, right? This is basically, that's how you find the average value of certain quantity. So we do this one quite often. If I want to find average energy, if I know the wave function, so you can easily calculate your average energy by doing this one. Very simple. We'll do a lot of examples. Okay, I think that's all I have to. So these are the things you will see time to time, so don't get nervous. So this is what we mean. Okay, so today we are going to talk about, actually real class starts from next week. That's where we started crystal structure and things like that. Before that, I want to give little introduction about what are the crystalline materials. You have single crystals, you have polycrystals, you have amorphous, you have even liquids, things like that, right? So first thing is crystalline solids. So crystalline means your atoms, they are arranged in very periodic way, right? So they have very periodicity. We call it's a translational periodicity. If you move from one place to other place, it looks the same, right? So that's basically, it's a regular repeated pattern, right? So we'll talk about that one later. So if you think about most of the important solids, they are crystalline materials, right? If you take silicon, if you take like perovskite or something, right? They all are highly crystalline materials. But there are so many important non-crystalline materials too. Amorphous, like silicon dioxide, that's the important thing, right? Oh, you can take aluminum oxide. These are good material, but they are not perfect crystals. They have some short-range crystallinity, but not long-range crystal. Crystals means long range. Even if you look at the scale, they have the same repeated pattern. That's what the crystals means.
So like a graphene lattice or
Yeah, so if you look at like graphene, entire graphene, right? So if you take one layer of graphene like this, how they suppose. So if you look at these carbon atoms here, right? I didn't draw it. So they all should look the same. Doesn't matter if you look at from this end or this end. It's the same repeated structure.
So like same in every direction, maybe, whatever direction you look at it from.
Yeah, it doesn't matter. So, but I'm going to talk about something called defects. So if this one is going to be interrupted by something, we call this a defect. There are so many defects like line defects, point defects and things like that. That we'll talk about that. Here I'm talking about perfect crystal, but there are no such thing as perfect crystals, right? There are always some defects, but you can make these crystals as good as possible. Remember, I don't know how many of you attended last year the Nobel laureate from he invented gallium nitride, the blue LED, so Nakamura. So his work was mostly to make gallium nitride as crystalline as possible, but nobody could make perfect gallium nitride, a lot of defects, but he managed to get as much as possible good crystallinity. So that was good enough to make the blue LED. So it's not like 100% good crystal, but less defects.
So would a diamond be a really good crystal?
Which one?
Diamond?
Yeah, diamond is we call this a FCC diamond structure. Yes, yeah, we'll talk about those things. So, but these are if you take small size, it can be perfect crystal, right? If you go to large scale, there will be some defects. Yeah.
But we still need these defects and more, like a lot of applications, right?
Yeah, actually, sometimes defects are useful. Yes, yeah, that's what people do. I'm going to talk about those things. To make a material strong, you have to alloy it, right? By doing that. That's a defect, but that makes things better. So alloying is actually a good thing, yeah. That's why I said crystal, it doesn't have to be a crystal to get all the good properties, but if you have the good crystal structure, we know how to change things, right? Put some dopants and things like that. Yeah, that's a good point, yeah. So also crystalline material calculations are easy, like Isuranga is going to do some, these two are theorists, right? They are going to do calculations. So if you have crystals, they are much easier because, so if you look at here is the same. You have to only think about the unit cell, this one, then you can translate it to the entire sample. If they are not crystalline, you cannot do that one, right? You have to consider the entire crystal. That's very difficult calculation to do. So here actually we are talking about this. Sometimes this class, if you go to different university, they might call this class condensed matter physics, right? Here we call the solid state physics. Condensed matter means it doesn't have to be just solid. It can be even amorphous, so even we call the short range or like liquid and things like that.
So is condensed matter more like water?
Yeah. It's not only modern, it can include things like polymers and things like that. So solid state, if I call solid, is mostly the crystalline and these solid materials.
Okay, so we don't want to talk about...
No. So we are not going to talk about polymers or anything, yeah.
What about amorphous?
What's that?
Oh, we're going to talk about amorphous.
Amorphous, not much, yeah. Some applications I will talk, but yeah. Yeah, this is all about solid state, yeah, that's right, yeah. So you can read all these things. So if you look at, everybody knows that the matter is basically gas, liquid and solids, right? So liquids actually now we can include even liquid crystals. These are highly crystalline materials, right? So gases, we know all the atoms and molecules, they don't bond with each other, right? There's no bonding because they have this thermal random motion, so they can move freely. But liquids, you can, even if they are not tightly bound to each other, it can take the shape of your container, right? If I put the liquid into the container, it will take the shape of the bottle. But gas you cannot contain like that, right? Unless you apply high pressure. So even applying low levels of thermal energy can easily break the weak bonds for liquids, and gases almost no inter bonding forces. So liquid you have weak forces. So that's why we can, by heating you can make these liquids evaporate, right? So I think these are liquid crystals. We have mostly, they have these dipoles, right? So typically if you take atom, you have a nucleus and you have the electrons, right? So these are neutral. We assume these pretty much spherical symmetry, but always this electron cloud, they can fluctuate and make some kind of polarization, right? So your positive and negative can be slightly off, right? That way. What is this one? It's the same, because we know this total charge is same as total, so your total charge is 0, but here total charge is 0, but they are separated. That means this is nothing but, we call it dipole, right? So this is dipole P. What is the dipole moment? Q times that separation, right? If this separation is D, this is basically dipole moment. So what's the direction? Always from negative to positive. Please remember that one. We are going to talk about these dipoles later. So if you have something like, say, positive, negative as a dipole, your dipole moment is always this way, from negative to positive. Yeah, so like I said, these crystals can be single crystalline, polycrystalline, or amorphous, right? So still they have very strong bonding between each atom. Like if you take gas, between each atom, there are no bonding, right? In the liquids you have very weak bonds. By even with little bit of heat, you can make them break apart. So definitely solids require more energy to break the bonds, right? So if you look at, yes, so polycrystalline, like if you, for simple thing, if you take this one, you can see this is a nice single crystal, right? If you take that whole thing as together, you can see this is one crystal, this is another crystal, but the entire thing is not just one simple crystal, right? This you can think as polycrystalline, right? So you can even, in a given area, you can have crystalline structure. Suppose if I have like this, maybe in this range I can have, say, atoms are arranged this way. That's crystalline. If you take this range, still it is crystalline, but in different the atomic configuration. So that means these are still, I can think as maybe this one like this. So this is as a whole is not a single crystal, right? But each one of them are crystalline. This is basically, that's a polycrystalline material. That's what this is about. If you take amorphous material, there's no any crystalline regions. There might be something smaller regions, like maybe something like that crystalline, then maybe nothing. So maybe few places you may have some crystalline, but these are long range, right? But short range there is no crystallinity like this one. So if compared to this one, this is like no crystallinity. Here there are like amorphous silicon. That's a very good solar cell because now people don't work on that one. Much cheaper, but compared to crystalline silicon, efficiency is much low. But amorphous silicon is a reasonable good solar cell. Yeah. So here is a single crystal. Later we are going to talk about crystal structures, right? This is how it looks in macroscopic scale. But if you look at the atomic scale, these crystals means they are arranged in really nice order, right? So this is actually more like this hexagonal close packed structure. So you can see, but they are this whole thing is a nice crystalline structure, right? If you look at in this ball wire diagram, this is what, right? So if you look at this one, these are nice. You can see entire the material has this crystalline structure. Later I'm going to show you how to pick something called a unit cell from this one. That's you have to be very careful how you pick the unit cell. It's not very trivial. So these are basically crystalline structures, right? If I had the polycrystalline, it doesn't look like this, right? In certain range, you have this arrangement, but it may be rotated, right? Yeah, here, single crystals, how they look like. This whole thing is a single crystal, right? It's in an amorphous background. You can see if you look at this one. So anywhere here, right? If you look at here, they are single. How about if you come here? Do you see anything above here? Nothing, right? That means that actually that's a kind of the imperfection of the crystal, right? If you look at anywhere here, it's nice, right? From every direction you have exact same structure. That's the crystallinity mean, right? If you look at from some point, you are surrounded by the same kind of atoms. So if you come here, you have the same thing. But if you can come here, it's not from top, there's nothing like that, right? That means the crystallinity is going to be broken at the boundary. So actually the air border is an imperfection of your crystal. Yeah, we talk about the polycrystals. You can see here. Yeah. So here you can see this is nice crystalline structure. This is, but these two are not the same, right? So here this is a crystalline. We have called these crystallites, like ranges of these crystals. So here is another example. If you have this the polycrystalline, these grains, sometimes we call these are grains. So then this border is called the grain boundary. So for example, this is my one crystallite or grain. So this is another grain, grain. Between that, we call these are grain boundaries. So there are a lot of interest in these grain boundaries. If we have polycrystalline material, how these grain boundaries can change. So each one of them is called a grain. One grain, and there's another grain here. These are all grains. So these are called grain boundaries. If you have these aggregates of these grains, we call this crystallites. Amorphous. Amorphous means you can see there's no order, right? If you look from here, so it's not the same here, right? Look at this one. In this red one, I have blue one to the right, but if you get this red one, blue is here is no same repeated unit, right? So that's what that one looks like here. The picture you can see is there's no repeated same unit here, right? You can see they are random. So that's, in real, they look like this. So there's no. Yeah, this is a departure from perfect crystals I was talking about. One cannot prepare a perfect crystal. Even the surface of a crystal is kind of an imperfection, right? Because it's going to lose that symmetry. Another thing is this, our third part of the class is we assume these crystals, right? If we have atoms to be like stationary or not moving, but at any temperature greater than 0 Kelvin, they always have some vibrational, we call some oscillations, right? So that's we call, if you have that one, you can represent that one as a wave, we call the phonons. So that means any thing, so above 0 Kelvin, they are not in this equilibrium position. They always vibrate about that equilibrium position. So, but at t equals 0, if you can reach, that's the only time you can expect it to be in equilibrium without anything. So next thing is, these crystals, you can have impurities. Like she said, sometimes those impurities are useful things. So there are two kinds of, two kinds of defects. One is called the point defects, other one or we call the zero dimensional defect. So that means if I take this, suppose first I take single element, suppose copper or something, only one metal. This is perfect crystal, right? You can see everywhere single crystal. Here is a missing, so it's supposed to be this one, now it is missing, right? So we call this a vacancy defect. So you are missing one, but this is for given single element one. So this is a pure metal, we call this a vacancy. Yeah, so then we should have, or we can call it important. Yeah, yes. Oh, here. Yeah, that's a vacancy. Then look at this one. So in this, these are the voids, right? So we can have extra atom sitting here. That's we call a interstitial impurity. So here we call the vacancy defect. This is a interstitial. Interstitial means between these two you can have additional one. Since it's the same material, suppose this is copper, we call this is self-interstitial. So this is a vacancy, here is the interstitial. So that's a defect, right? So now if you take alloy means two different metals. Suppose you have copper, then if I take different atom, say maybe boron or something, if you put it in the interstitial here, this is the interstitial voids, right? Here. If I put a second metal here, that's also just like interstitial, but that's not self, right? It's a different one. So we call this a substitutional impurity. So that's a different one. Suppose in copper matrix I can put a boron atom or something.
Would that be like doping?
What's that?
Would that be like doping?
That's kind of doping, yes, yeah. Because you can, by doing this one, you can make some electrons to the share, right? So that way you can put, yeah. So for silicon, put in boron and phosphorus, that's how you dope it, right? P-type and N-type, yeah. So then also you can have yeah, so this is yeah, here again what is this one? I cannot even see. Interstitial impurities, substitution, yeah, oh, here, this one and this one. So I can dope different metals, substitutional doping. The substitute means everywhere is the same thing. One of the atom I can replace with a different kind of atom, like this red one here. It doesn't look very clear, right? So that's the red color. It's clear in my head. Yeah, this is the substitutional, the doped one. Substitution means you replace one of your original atom with a different atom. So that's a substitutional doping, or you can have interstitially different atom. But in order to have substitutional dopant, what is the requirement? The ionic radii should be similar size, right? Yeah, because unless this is really small, you cannot have substitutional doping. Then it can only be the interstitial doping, right? If this is too big, it won't fit in here, right? So to have substitutional dopant, you have to first compare the ionic radii of these elements, then you should try that one here. For example, now we are doing experiments like arsenic phosphide, right? So these both have somewhat similar size. Then it's easy for us to replace arsenic by phosphorus by arsenic.
Okay, so you can't like dot with similar with a, you know, you can't just dot in general with bigger or smaller.
Yeah, so but it can be slightly different, but cannot be huge. If you take the periodic table, right, going from yeah, then all these. So if I want to replace something, fluorine with lithium, lithium is much smaller, right? That can happen here. If you go down here, right? So like if you take so down here, so if you go this way, then the size is changing, right? So then you cannot expect something in this size to do the substitutional doping, right? It has to be somewhere in this vicinity. So they have quite close ionic radii, right? But you can do the substitutional, interstitial doping by putting something here and going here. Then first you need to, if you are planning to do something, first you need to compare the ionic radii, the values.
Okay.
So like we were discussing for pure metals, so these making these vacancies are very important for diffusion. So because these ions can move, like if you take a lithium or sodium ion, so solid state batteries, right? We have lithium, lithium ions have to diffuse, right? To diffuse you need to have vacancy, right? Then only that one can jump to this one. Then you need to have another vacancy for the lithium ion. So for diffusion, vacancy is very important. So the oxygen vacancies, these things are really important for ionic conduction. So that's what we call this important for diffusion.
Would it be like?
Yeah.
Is it the same for catalysts?
Oh yeah, exactly same thing. Yes, yeah. In the catalyst, it's mostly from the surface, right? Yeah. Still, you need to have some vacancy. Yes, yeah. Catalysis is this ionic conduction, especially for batteries, fuel cells, all these things. These vacancies are really important. People intentionally make these vacancies. He's working on this catalysis, so that's something we need to work on this the vacancies. So this for alloys having this both substitutional and interstitial doping, that can enhance the strength. So even things like the ductility or malleability kind of thing, so you can improve by alloying with different metals. That people do very yeah.
Do you have to have like periodic vacancies?
No. So no, if you want to have the ionic conduction, yeah, you need to have many vacancies, because what happens is it jumps from one place to another vacancy, right? So from that vacancy to another vacancy, yeah, you need to have a continuous path of vacancies.
Oh, okay.
That's how, like if you take a lithium ion, if your lithium ion has to move from, we call the hopping mechanism, right? So it has to hop from one vacancy to another one, from here to, thing is once it hop here, it can create another vacancy somewhere, because what is happening there, so it can replace one atom, so that it will help you to hop into the next one. It's not important having just one vacancy, right? You have to have series of, basically making a percolation path can have the conduction. So then there are something called the line defects. Those are point defects, right? So line defects, there are two kind of line defects. One is the edge dislocation. Edge dislocation means just imagine this is a perfect crystal. Say you have 1, 2, 3, 4, 5, 6, 7, right? Now if I, up to here I have 1, 2, 3, 4, 5, 6, 7, right? Now half of this atom plane is missing, right? Now I have 1, 2, 3, here, 3, 4, 5, 6, right? That means this middle atom plane is missing. Then what happens? So these outside planes will collapse towards that missing planes, right? So then your whole crystal becomes kind of buckled. So we call this is a edge dislocation. It's a line dislocation. So you can see typically this direction, this perpendicular direction is called the dislocation line. So that is basically edge dislocation. So then there's another dislocation called the screw dislocation. The screw dislocation means you take your crystal, then suppose if you cut it into half, then you just do like this. So suppose if I cut by half, then rotate like this, then you do something like this, right? Then you just rotate like this is kind of rotation. Then you have, again, your whole crystal structure becomes distorted, right? So that's the screw dislocation. If you look from top, it will look like this, right, in this plane. Again, this is called that dislocation axis here. So when you talk about these dislocations, people use something called the Burgers vector. So Burgers vector means if you have perfect crystal like this, suppose if I go from this end to this end, you go, suppose if you go from here to here, 1, 2, 3, 4, then you go down 3, you go exactly 4, right, and 3 up, right? It closes your loop. But if you have a dislocation, what do you expect? If you go the same distances, it will not close. You will have some gap, right? So that's the vector joining this, the remaining distance is called the Burgers vector. So in this case, so suppose if I start from here, you go 4 here, 3 down, 4 here, and 3 up. So it closes, right? Your Burgers vector is 0. But if you go here, look at this one, I don't know how here, you can think about here. So now this is a edge dislocation, right? Because I took out half of the plane, so this is buckling. Now if you look at, if I measure from here, say I go 1, 2, 3, 4 this way, I go 1, 2, 3 down, 1, 2, 3, 4, then I go here, exactly 4. Now this is the end, this is the initial. They are not closed, right? So then this, we call this one as the Burgers vector. I get the same number right here. If I start from here, to the left I am going 4. So let's see. If I start from O, right? So to the left you get 4, right? Here 1, 2, 3, 4. So down I go 1, 2, 3, right? Down you go 3. Then this one I go 1, 2, 3, 4. Exactly. 4 here, this way. Then again you go 1, 2, 3. So you went exactly same numbers, but it didn't close, right? Previously when I did that 4, 4, 3, it closed here. Now when I went here, it didn't close. So this is the original one, this end. So that is called Burgers vector, that initial and final opening. So same thing here. So this is the screw dislocation. Here what I did was, I take this crystal, I cut in half and just move it around, right? That's how you made this one. Now, if you look at this one, you will see, you can calculate this one. So if you go 2 here, this way, and this way, if you go that one, I think it's going to be open, it's not clear. So then you will see actually, I think this will be the Burgers vector. It's not, no, actually in the next one I have very clearly. So here it's hard to see. Look at this one, then we can see very easily. So this is clear for everybody, right? So this is, what is this one? This is the edge dislocation, right? So you don't have that middle plane, that's why they come with this the dislocation axis. This is how it looks in the crystal structure, right? Because these things come together. So you can see, so this is for that line dislocation. You can see this is my Burgers vector, right? You get 2 this way. When you go here, it ends here. This is starting, this is the Burgers vector. The L means your dislocation line. That's why you rotated this one. Here, you can see the Burgers vector. See, I start from here, right? I go 2 this way, down 2. This way I go 4, up 2. When I go here, your 4 is done, right? 2 this way, 4 this way, here again 2. Now 4 and 4 is all done, but it's didn't close, right? So that means this is your Burgers vector. If I didn't have this one, it closes like this, right? Burgers vector is 0. Yes, Burgers vector is the easiest way to see what the dislocation is. Oh, these are all about vectors, right? Then we talk about the grain boundaries, remember? So we have, these are grains, right? So this is one whole grain. This is a nice big grain, right? Whole thing, but this is a different grain. This is also another different grain. So here's a different grain. So these are, we call, what do we call these? Grain boundaries, right? So you can look at these grain boundaries. Typically what they do is, so if you look at the grain boundary, they draw the normal to that grain boundary. So then this is the angle of misalignments. So here again same thing. This one you draw this normal to this one along the line. So this is the angle. That's how you define the misalignment of each grain. So here misalignment is much larger, right? Between this grain and this grain compared to this grain and this grain is smaller. So that misalignment angle is what defines you the how they are not perfectly aligned. They call the misalignment angle. Okay, so that's all. Any question from this one? Again, these are very basic things you must have learned before, but for some people might be a little bit new. So now next thing is again very something you may know, interatomic forces, right? So how you hold a crystal together, right? So basically if I have atoms, so typically these atoms are neutral, that's good, right? If they are neutral, it's easy to keep them together. But always there are some like charging effects, and also when you bring 2 atoms closer, what is really happening? So you have from one atom, you have all the electrons, right? Suppose this is the nucleus, you have these atoms. So this is also nucleus, you have all these atoms. So they are fine, right? So they are neutral atoms. But if you bring this one too closer, what will happen? So these electrons are going to kind of share between. That means actually the 2 electrons will try to occupy the same energy states. So actually that's something we didn't talk about. There's something called the Pauli, what is the exclusion principle. Pauli exclusion principle says, remember we talked about this states N, L, then ML, then spin MS, right? These are the principal quantum numbers. So no 2 electrons can have the same 4 these numbers. So you can have all 3 same, but at least one has to be different. But no 2 electrons can have all 4 same. So if you bring these two atoms really close, so these two electrons, we know from each they have their own these numbers, so they may try to occupy the same state, right? So that means it's not allowed. Then what can happen? So then it will try to repel it. Right? It doesn't let you come any closer.
So you're trying to put it together like a boson, maybe, like where you can just.
If you have bosons, there's no.
Right.
Yeah. If you have bosons, that's why you have the something called this Bose-Einstein condensation, right? That you can occupy all the ground state here. But fermions, you're familiar with the bosons and fermions? Probably not. Fermions, electrons are fermions, so that the Pauli exclusion principle is basically valid for fermions. But bosons, they can occupy anything, they don't care. But we are going to talk about most electrons, right? Yeah. So that's the thing, like if you bring these atoms quite close, then it will try to repel, right? Because otherwise it will violate the, but even the atoms, when they bring close, there will be some charge redistribution because the electrons are going to be shared. That's why you need to have some interaction, right? To keep it closer. Then also you have to have this repulsion, that one also, to avoid the Pauli exclusion principle. So that gives rise to the different interatomic forces. That's what we are going to talk about.
So darn half integer spin.
What's that?
The darn half integer spin. Creating fermions.
Spin, because of spin, it allows you to get that close. If you don't have that spin difference, then it won't even let you get that closer, right? Yeah. So if you look at this, interatomic forces is what kind of forces hold the atoms together, right? We know atoms, but how do you keep them close? So in a compact crystal form. So there are many forms of these forces. So first thing is, you need to know something called, very important quantity called cohesive energy. Cohesive energy means if you have these atoms together, so this is the crystal, right? Cohesive energy means cohesion, right? Together. So you define that cohesive energy as the energy of this system minus, so actually this has the lowest energy, that's another thing, right? Always systems like to be at the minimum energy state, right? So that's even, we do the same thing, right? So we like to be at the lowest energy state. So if these are separated, so they have much less energy, right? So the cohesive energy means the energy of this system in the crystal, the bonded the entire crystal, minus if all these atoms are completely separated, they are no longer interacting with each other. So that means you need to provide enough energy to, actually this is at the lowest energy, right? So that means you need to provide some energy to make it separated. So that energy is called the cohesive energy. So cohesive energy is mostly for, we are going to talk about these different bonds, like probably you all know, like covalent bonding, ionic bonding, metallic bonding, and lastly the van der Waals bonding. So the strongest bond is the covalent bonding, right? So covalent bonding is, like I said, these electrons are going to be shared by each other. So ionic bonding means these two will have some charge exchange. That means one becomes positive, one becomes negative. That will make it attractive, right? Because you need to keep them together. But also you cannot get it too close, then it will try to repel, right? So otherwise it will be, if it's attracting, it will be pretty difficult, right? It becomes kind of equilibrium position. The interactive force and the repulsive force are going to be in equilibrium. So we'll talk about that one later. So remember, cohesive energy is clear for everybody. Cohesive energy means the energy that must be supplied to the solid to separate its constituents into that free form, right? There are no charge separation or anything. But if this cohesive energy is for ionic crystals, that has a separate name called lattice energy. Please remember, a lot of people get confused. Cohesive energy is the same, but if you talk about cohesive energy for ionic crystals, that has a name lattice energy. Lattice energy is same as the cohesive energy, but it's only used for ionic crystals. Please remember this one. Lattice energy of a solid, it is the energy that must be supplied to an ionic crystal. So we'll talk about ionic crystal in the next one. Please remember that one. Lattice energy, if I talk about lattice energy, that means that's the ionic crystal, not covalent, not van der Waals, not metallic.
So it's cohesive just for covalent, metallic, and van der Waals?
Yeah. So for those, typically we use the cohesive energy term. But if you talk about the ionic, for some reason they don't use the cohesive energy. They say it is a lattice energy.
Do you know why? Is that just?
And there must be some historic reason where I don't know. Yeah. So these are the ones we are talking: ionic bonding, covalent, metallic at the end. So they are very weak bonds called hydrogen bonds. Anybody remember the hydrogen bonds? That's ice, right?
Yeah.
Ice is a crystal, right? So water molecules, so they are bonded by hydrogen bonds. Yeah, so ionic bonds are the interatomic bonding. You can read all these things. Also, going from strength, van der Waals bonds are the weakest bonds. We are talking about like 1/10 of electron volts per atom. If you go to covalent bonds, we are talking about more than 5 electron volts per atom. That's huge energy, right?
Van der Waals bonding would just be like in graphite.
Yeah, between the graphene layers, yeah. Then also you have like, if you take a like gas crystal, the argon crystal, if you low temperature, argon are going to be crystal like that. That's due to van der Waals forces. We'll talk about all these things in more details. Yeah, please read all these things. Yeah, the covalent bond, the ionic bonds, good example is sodium chloride, salt, right? So if you take chlorine and sodium, so if you bring these together, so actually you will have some charge exchange, right? Sodium becomes positive charge and chlorine becomes negative charge. You have two positive and negative charge, what do you get? They attract each other, right? So then they come together. So then why does it sit like nice compact? Because of that repulsion force, right? That they have interaction, but when it get that close, you have repulsive force. So we'll talk about that one. They come to an equilibrium. That's why they become nice crystal. Here, this is what happened, right? They come here, so then many of these come, then they kind of make the bond. So what happens is, these are basically electrostatic force, right? I think everybody knows what is the electrostatic energy and electrostatic force, right? So if you have two charges, if you have positive, say Q and negative Q, positive Q. So if positive negative, they are going to attract each other, right? So if the separation is R, your attractive force is given by this 4 pi epsilon 0 Q and Q, that means Q squared, right? Divided by the R squared. This is actually depending on R, right? So if they are different charges, they are attracting each other, right? So what is the potential energy? If you have a force, always you have the potential energy, right? Potential energy is given by this minus q squared divided by same this 4 pi epsilon 0 times r. There's no r squared here, please remember that. That is between two charges, but they are opposite charges, they always attract, right? So that is the typical force and the energy. That force is enough to keep them together, right? So, but when you count, you have that much energy. We'll talk about all these. Yeah.
Yeah, can you explain again the terms and the force? This one?
Yeah, this for the force.
Yeah, what are the terms again, please?
Oh, this Q is a charge of each, because in this case they both have the same charge, right? If they are different charges, Q1, Q2, yeah, that's a good question. Yeah, Q1. Yeah, let's try this one in a more general term. If I have one charge Q1, another charge Q2, separated by distance r, force is given by Q1, Q2 divided by 4 pi times epsilon 0 times r squared. So then this depends on your, if they are same charge, they repel. If they are opposite charge, they interact, right? So this epsilon 0 is a constant given by 8.85 times 10 to the power minus 12 or 9, 12, right? 12, I think unit is in K is newtons per coulomb squared meter squared. Yeah. So this is a constant called the that's correct, right?
Yeah.
Yeah. So K, inverse of K, right? K is Newton per Coulomb squared meter squared. Yeah. So this is a constant.
Yeah, I just need to replace one.
So Q1, Q2 are the charges, and R is the separation between this one. So if you look at that force, actually it goes like this, right? When the distance is increasing, your force is the magnitude of the force, right? So this is the magnitude. It's going like 1 over r square. We call the inverse square law. If you look at the potential energy between the two, that is given by Q1, Q2 divided by 4 pi epsilon 0 times r. No. So this is typically in newtons. This is in joules. There are no r squared here, because we know typically this U is given by F dot ER. Potential energy difference is, that's why if you differentiate this one, integrate this one, you get R squared. Okay, so now we talk about this one. So this is exactly what happens, right? Is that clear for you? This you should. So if you take sodium, we have this outermost orbital, you have only 1 electron. If you take chlorine, outermost one has 7 electrons, right? 1, 2, 4, 5, 6, 7. So to make it saturated, you only have to give away 1 electron. Then this will be happy and this will be happy, right? So that means this will give, means this becomes singly positively charged, this becomes singly negatively charged, right? So that's why they have same charge, so they interact with each other and make attracted to each other. So but when they come closer each other, so that the orbits of the electron in the ions begin to overlap, then they try to occupy the same state by 2 electrons. So then Pauli exclusion principle says, no, you cannot do that, right? Keep it away from me. So they have repulsive force. So if you look at this one, so if you draw this energies, oh yeah, we can draw the potential or the energy. This is the easiest way to understand. So this is sodium and chlorine far away, so they don't interact each other, right? Now we are bringing them closer, then what happens? They are going to interact, right? So that means you have this energy given by this your charge Q1, Q2 divided by 4 pi epsilon 0 R, but Q1 and Q2 are now different, right? One is positive, one is negative, then this becomes negative. That means that the attractive term is always negative. If you look at the total energy here, so this is your zero energy, so this is always negative. The equation is 1 over R. If you draw this one, this is your total energy as a function of R. Far away, no interaction, right? It's 0. Now we are getting closer and closer, then it's going, getting negatively large, right? 1 over R, like that. But you don't get to 0, right? So because before you get to 0, what happens? They are getting too close, then they want repulsive energy. Repulsive means this part becomes positive. So when it gets quite close, now repulsion is going to take place. Repulsive means this is becoming positive like that. So if you look at these two, if you add these two, what is the total? So you have this one here, you have only this one up to here. So then here is negative one is going to be a little less negative. So when you come here, this becomes even more less. Then it's going to be positive. So then it's going to go up like that. So at this point, your repulsive and attractive force are going to be equal, right? Yeah.
Oh, is that curve called the effective potential?
What's that?
Is that curve called the effective potential?
Yes, yeah. So this is your, this green curve is your attractive force. This red curve is your repulsive force. Then if you add these two, you get this purple curve. You can see. So this is the place where your du over dr are going to be 0, right? That's what this problem is. You would calculate du over dr. I give you du, this e here is, u means e here. What you have to do is take the derivative and find where it becomes 0. So then you can find what that distance. That is the place is going to be in equilibrium. It cannot get any lower or it cannot get any higher because already attraction is taking place. So for sodium chloride, this is something like in femto, I think 236. Yeah. So here is the equation I was talking about. This is true for any, not just something that has the atomic number A, CA times CB, so that's nothing, but important equation is 1 over 4 pi 0 times R. Is that clear for everyone? That's the equilibrium separation. Okay, so now let's calculate simple energy. This is just for 2 atoms, right? But if you have a crystal, what do you have? You have many atoms, right? That's actually second problem is how to calculate that one for 3-dimensional case. I will do this one for 2-dimensional case. How do you calculate that one? Suppose this sodium chloride. So I have sodium, then chlorine, sodium, chlorine. So one is positive, other one is negative, positive, negative, positive, negative, like that, right? So I start from here. So negative, positive, negative, like that. So this separation is say R. So that means from here to here it is 2R, right? So from here to here it is 3R and so on. So now let's calculate the total energy. let's calculate this. You just pick one and calculate the energy from all the other atoms. That's not difficult, right? So they all have the same positive negative charge. So just take this one. So what is between these two? Can you write the energy? Suppose it's E squared, right? This one has E, suppose this one has minus E. That means you have minus E squared, right? Remember this equation is energy is E squared over 4 pi epsilon 0 R. Let me put it. Yeah. What I have here is between these two minus E squared over 4 pi epsilon 0 times R. How about this one and this one? 2R, but that's positive. So that means this becomes positive, right? Positive E squared over 4 pi epsilon 0 times 2R. Next one is negative. Negative E squared over 4 pi epsilon 0 times 3R plus E squared over 4 pi epsilon 0 times 4R and so on. Right? So this is infinite series. If you do this one, you get minus E squared over 4 pi epsilon 0 R times what you have here. You have 1 plus 1 over 2 minus 1 over 3 plus 1 over 4 minus 1 over 5 and series. Anybody remember this one? Probably high school math series.
I don't think it's the pi square root 2, I think, or 6, I think that's right.
So this is very
Yeah.
known series. It's a convergent series where positive, negative, right? If you do this one, this is nothing but log 2.
That's
Yeah. So this series 1 plus 1 over 2 minus 1 over 3 plus 1 over 4 minus 1 over 5 plus 1 over 6 minus 1 over 7. If you do this to infinity, this is actually log 2 log 2, I think. Something like that. It's a convergent series, that's the important thing. Here this one, please go through and do this one. Yeah, 2 log and 2. 1 minus, maybe I made a mistake. Yeah, this is this other way, right? Minus half plus minus plus. You get the idea. Because I had this negative taken out, right? Then this becomes negative. Yeah. So this series is, no, I think this is a log game too, sorry, yeah. Because you had, oh, I made a mistake, yeah. No, that's not the mistake. So this, I only considered this part, right? So you have the same thing. This one is nothing but 2 times, right? Every time I got this one, then I have same thing here, that I have another term 2 here. Everything becomes, please remember that one. You have 2 times this one. Is that clear? Well, I only consider right side, right? But same thing to the left, to the infinity. That means if you do that one, please follow through this one. What you get is, the 2 comes because we measure left and right. So that series sum is just log 2. Yeah. Here is the final equation. So don't worry about the C number. E squared over 4 pi epsilon 0. E squared over 4 pi epsilon 0. Then we have 2 log 2. So if you have, this is just for simple one-dimensional ionic crystal, right? So typically, if you write something like this, so for any crystal, if your the total ionic energy, not the ionic energy, total this energy. So this is more like a lattice energy, right? But lattice energy means for 2 particles. No, actually this is the total, the lattice energy, to how much energy you need to keep them together, right? This ionic crystal. So this total energy is given by minus E squared over 4 pi epsilon 0 times this, say R. Then you have this number M. That's what we have, right? In our case, this is minus E squared over 4 pi epsilon 0 R times 2 log n2. This is standard expression, right? E squared over 4 pi. So this M is called the Modellan constant. It's just a unitless simple number. So in our case, what is M? M is 2 log 2. M is for sodium chloride one-dimensional case, right? One-dimensional case. That's what we did, right? This M is simply 2 log 2. So this is M is for the, yeah. So ideally, so for the example I gave you like 3-dimensional case, so then you can easily find. So in this case, if you take some, you will see how many atoms around that one, then you have to, I gave number of atoms, so you don't have to 6 clearest thing, closest 6 atom, then 12 next neighbor and things like that. So it's very simple, it's simple geometry, it's nothing. So
is it just like the convergence series, just different?
yeah, but in this case actually this is not really convergent very easily. Yeah. That's, I want you to see whether it's converging or not. It's a very slowly converging one. But if you do that problem, actually in the first part, you will get this number. So first part is, I gave all the information, you just calculate this is about 1.75. Yeah. Oh, you don't have one. I already put it in the Blackboard, yeah. Because in Blackboard you can see the color. This one is easy to do the calculations. Is that clear? So if you have something like this expression, well, this is the potential energy for 2 particles, right? So whatever the additional factor is the Modellan constant. It's a unitless number. Okay, then the last thing I want to talk about is, what's the time? There are 2 quantities everybody should know, something called the ionization energy and the electron affinity. Ionization energy means if I have, we'll do this example and stop that. If you have atom, so nucleus, then you have electrons, right? So ionization energy means how much energy is required to remove 1 electron from the atom. That means if we have A atom, that becomes A plus ion, plus electron. So this energy is called the ionization energy. That means how much energy is required, you have to supply that energy to remove 1 electron from the system. That's a positive energy, right? We have to supply. This is the ionization energy. Affinity means, for example, this is like a sodium, right? Yeah, removing 1. So electron affinity means how much energy is gained by receiving 1 electron. For example, chlorine. Chlorine is getting 1 electron, right? So that means basically A becomes A minus, right? By actually in this case, yeah, A going out. So this one, A becomes A minus electron. Right? Yeah. A minus electron becomes, sorry, A plus electron. A receives this electron and become A minus, right? So this is the electron affinity. So this is called the ionization energy. Just remember these 2 words. So that means if I have this sodium chloride or whatever, right? A plus B minus. So what is the total energy you want? If you want to make the sodium chloride, right? So this sodium chloride, right? So what is the total energy you need actually? You need the ionization energy for sodium, then you need electron affinity for chlorine. Is that all? Yeah. Then you need the electrostatic energy. These are the three things you need to keep the crystal together, right? So that's what this is all about. So for example, let's do one example. If I want to do, say, this alkali halides. Say, alkali halides are very important ionic crystals. So even silver iodide and all these are ionic the alkali halides, but they mostly these are from the alkali metal series and these are from the halogen series, right? So chlorine. So we just take one. This is still like sodium chloride, like that, right? So if you take one example, rubidium bromide. So you can see the rubidium bromide crystal here. So to keep this rubidium bromide crystal, how much energy is required to supply, or how much energy required to form this crystal? So for that, what do you want to know? First, you need to know what is the ionization energy of your rubidium, right? So that is given as 4.2. But what is that? It's a positive number, right? Ionization energy is, you need positive 4.2. Positive 4.2 electron volts. Then if you take bromine, that's getting -1, that's the electron affinity. That electron affinity for bromine is given as 3.5, but that value is what? It's a negative value, right? -3.5. Now if you take the sodium and chloride, so you need to know what is the electrostatic interaction. What is that value? So that means your total energy is 4.2 minus 3.5. Then you need the electrostatic energy. What is that number? E squared over 4 pi epsilon r, right? So that is that. What is that? Positive or negative? Negative, right? You have positive charge and negative charge. Negative E squared over 4 pi epsilon 0. What is that R? That's the equilibrium separation, right? If you look at this one, this value, this is the equilibrium separation, right? Because that's, yeah. So that value we know for rubidium bromide, that's RB is given as 0.34 nanometers. So then you can calculate everything, right? If you do that one, you will get your delta E as plus 4.2 minus 3.5 minus E squared over 4 pi epsilon 0. R0 is this one. If you put everything, you get 4.2 electron volts.
You also need that constant.
What's that?
You also need that constant.
No. So this is just to get for only one the bit, because we are only considering one electron moving. This is for only two atoms coming together. It's not the entire system. Yeah.
But like if you consider it like, more, for
Yeah, if you want to put all this together, then you have to multiply by this one you have to multiply by your modeling constant, right?
Okay, so like everything.
Yeah, then these things you have to multiply by how many number of atoms they are there. But here we'll just simply calculate the this delta E value. So important thing is this delta E value should be negative. If it is positive, you cannot have the crystal structure, right? It's like a Gibbs free energy, right? You need to have Gibbs free energy to be negative if you have that reaction happen, right? Just like that, your total energy has to be a negative number. If you calculate this one, this is a negative number, because that's the lowest energy configuration. Right? Crystal has the lowest energy, right? That's why that's why you have to provide that cohesive energy to separate all the elements. I think it's almost time, right? So next time I'll talk a little bit about covalent bonding, and then we'll start the real solid state physics. I need about 5 minutes to go through this one. It's already 50. So please go through this one. If you have any questions, send me email or come and see me. Yeah. Like I said, you guys can get together and that's the best way to learn actually. Yeah, you can talk to these guys and work with them. Yeah. Otherwise, come and see me. Yeah. All these lectures are in the blackboard. You can read and. Like I said, doing homework is the only way to learn what you did in the class. Also, there's one student, so she asked whether we can give this missed 2 classes. Maybe if you can send me the 2 lectures, videos, I can forward to everybody maybe, right?
Sure.
Can you upload into our Blackboard?
The first one's already on YouTube. I can send you.
Okay, just send it me. Yeah. Then I can even upload into the
Yeah.
Blackboard, right? So you guys can read it. Yeah.
I'll do that right now.
Yeah. Okay. Good. Yeah. Okay. Have a good weekend. Yeah.
Oh, can I get your email? You have your study? I was going to see the YouTube channel and our entire Discord channel where we talk about homework and all things like that.
Did everybody get this one?
Yeah.
Yeah.
I guess this is.
Yeah. But anyway, it's in the
Oh, okay.
Blackboard. You don't need that. Yeah.
Oh, it's just one sheet.
Yeah. Yeah. Both sides. Yeah.
Alright.
We have another class now, right?
Yeah.
Okay.
7 minutes.
Oh, you have 7 minutes. Usually what time this class is over? 45. Okay, so this is a little bit.
Dr. Green,
Yeah.
could I come to you?
Yeah.
Sometime next week. I don't know what time yet.
Yeah.
Could I just talk you through everything?
Yeah, definitely.
in
Yeah,
preparation
that's
for,
what I
like,
want students
and
to
like,
do.
well, no, in preparation for qualifiers.
Oh, sure.
I'm like stressing out. I just want to make sure I,
Yeah, come and see me.
the majority of the fundamentals.
Yeah. How about maybe Monday or something?
Sure.
Just send me email before you come.
I will.
Then I will, yeah.
I'll confirm the time with you.
Yeah. Okay.
I'm so stressed. Ooh, magnetization. Ooh.
Try to.
Let's find the magnetic moment of it. Oh
It's
my God.
very strong magnet.
Yeah. If we have a current going through here, and this, this side on this side, this is the area. This is the magnetic moment. Yeah. So if we have a marker.
Oh. Try this. Do this.
Or you're doing just the magnitude of this things. This is your magnetization. These are your magnetic dipole moments.
QD. Oh, sorry. No.
This is magnetization. For electrostatics, there's that torque. I don't want to miswrite that, but for a dipole moment, for electro dipole moment, and that's a QD. This is your.
I just start with columns.
Yeah. Just work everything out because pretty much that's all it is. I'm just gonna grab everything from that. Your CV or your potential difference. you start just like, you would find the electric field from like here to here, here to here, and you would add them so like these are vectors, so like these are the components. The horizontal components cancel out because they're in the same direction, same charge, and you add the two vertical components, so you would get the electric field E1 if Z2 is like 2Q, like Q squared, whatever.
And what if
Oh, for a line charge.
yeah.
Oh, okay.
Use distribution.
It's a similar. The line charge, you would just have to redefine what Q is. So dq, so the line charge is just dl over lambda. So you would just and you redefine everything in terms of that, and then you plug it into
Q is on the DL.
yeah because the line charge is a charge per charge per unit.
Yes.
Yeah, whatever. Yeah.
You are having that to integrate over.
Yeah. So you just find the electric field, just normal kind of almost seven
On the 2 point.
well, for with respect to.
Usually
Oh, yeah.
and
Yeah. So that's your
dx, the distance x from
Right.
0, and then you integrate from
yeah. Once you do like 3 of them, it's, like, it's almost all the same.
I just did it from here.
This microphone works. I test.
Started with Coulomb's law,
Yeah.
electrostatic potential energy, the dipole moment, electric dipole moment.
Join us on the weekend, and like we already doing this all day, every day.
When?
I don't know. You guys want to meet Saturday, Sunday, every day?
Yeah. I'm ready for every day.
Not Friday though, because
Friday we have, I'm
Friday
sure
I have
we have
meeting.
meeting at 2, I think, this Friday.
yeah, but like you guys should all come. Like when you're done your meetings at like 3:30.
2 to 3 lab तपाईँको छ होला हैन?
Meeting.
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 2 बजे.